Good afternoon. My name is Marica and I'm a third-year PhD student at Queen Mary University of London. Today's talk is focused on my second-year project, the Maxwell-scalar field system near spatial infinity. The aim of this project is really to understand how the nonlinearity of the system affect the regularity of the solution and polyhomogeneous expansion near spatial infinity. In particular, the critical set with spatial infinity meets null infinity. This project is a part of a bigger plan, which is to want to study the problem of spatial infinity. In particular, what we wanted to do is to use this project as a toy model to develop a technique to be used later on to study the linearized version of the Eisenfield equation near spatial infinity. In the standard representation of spatial infinity, we have the Minkowski metric, and spatial infinity is simply the area contained in this domain, the tilde, which is the complement of the null cone via the origin. What we do is to use Friedrich representation of spatial infinity. This means that we use some inversion coordinates together with the conformal rescaling, so that spatial infinity becomes the origin of the domain in the unphysical space-time. But what is peculiar of Friedrich representation is the use of the F-gauge. With this F-gauge, introduce this new time component, new time coordinate tau, so that a conformal representation of Minkowski is given by this rescale metric. In particular, this metric contains, in this case, we have the spatial infinity it blows up, and we have the structure of the cylinder at spatial infinity. If we on the right-hand side of this page, you can see the structure here, which corresponds to a longitudinal slice of the cylinder. You can see I plus and minus that correspond to the critical set where the cylinder meets future and past null infinity, and I in zero, which is where the point where the cylinder meets the initial hypersurface. In this setting, we introduced our system, the Maxwell-scalar field. This is given by the Maxwell equation together with the conformal invariant wave equation, and they are coupled via the covariant derivative. Our technique consists of introducing a conformal rescaling, so that from now on we'll work on the corresponding unphysical quantities involved in our system. Then all the resulting quantities will be then expressed in a spinorial formalism. So we will introduce the Faraday spinor, which is the spinorial counterpart of the Faraday tensor, and the Maxwell spinor. To exploit the symmetry properties of our problem, we introduce a Forte decomposition in terms of space spinor. This means we have a spin diode here, and we introduce a time-like spinor, which is the spinorial counterpart of a time-like vector tangent to the curves. And then we could decompose all the quantities using this object. In particular, as you can see here, we have the gauge potential. In the end, what we do is to have a frame formulation of all these equations with this Neumann-Peirce frame, which is a frame adapted to the cylinder. And so that our set of equations reduced to the following, where black box operator is the F-reduced wave operator in Axon scalar as follows. The set of equation then is studied in its decoupled and coupled version. In particular, I would like to point out that all the quantities here are spin-weighted quantities. At this point, what we do is to then study asymptotic expansion of the quantities following Friedrich, an approach that is used by Friedrich in the context of the conformalized field equation. And this approach relies on the key observation that these quantities, upon evaluation on the cylinder, gives a set of transport equations. So they allows us to relate the property of the initial data on an initial hypersurface with the radiative properties of the solution at spatial infinity. When studying the decoupled case, we have that our system reduced to the following. And so at this point, we prescribe an expansion in spherical harmonics. By replacing then these ansatz into our system, our set of equations reduced to these three model equations, which are Jacobi differential, ordinary differential equations. The behavior of the solution depends on the value of L. In fact, on studying the solution, we see that for L between 0 and p minus 1, all the solutions, so the solution of the three equations, are just a combination of Jacobi polynomials, where all the coefficients can be expressed in terms of proper initial conditions. Now, in the case L equal to P, we notice that the solution to the first equation behaves nicely until the coefficient C2 is equal to 0. For C2 different than 0, we have a logarithmic behavior at the critical set. So we worked on the solution to try to figure out how to avoid this logarithmic divergence. And in this case, we noticed that time-symmetric initial data guarantee the vanishing of these coefficients, and so the solution behaved nicely. For the other two equations, we found a similar behavior. In this case, we have to use, we have again the problem of logarithmic divergences given by C4 and C6. In this case, we had to prescribe an extra condition obtained by using the Maxwell constraint equation, and it relates the derivative of the solution and the initial value of the solution together with the initial data of the solution for the solution and its derivative. Since the other equation, the solution to the equation B is also solution to equation C by sending tau to minus tau, so they're related by time symmetry, we have a similar condition for the last equation to avoid the logarithmic behavior. So we can summarize the behavior of the solution of the decoupled system with the following proposition. We have then a polynomial dependence in tau for L between 0 and p minus 1, and so the solution extends analytically through the critical set. But generically for L equal to p, the solution has a logarithmic singularity at the critical set, but this logarithmic divergence can be precluded by fine-tuning the initial data. After this, we moved on studying the coupled case. The study of the coupled case started with the study of the zero-order transport equations. So we took our set of equations and we evaluated them on the cylinder. This is the reason why we have this black triangle. This is simply black box evaluated on the cylinder. The corresponding set of equations at the zero order is the following. This equation actually decouple, and we have also found a lemma that provides a unique solution to this system with suitable initial condition. This lemma is fundamental because we use this to construct the solution to higher order transport equation. In particular, we studied equation for p greater than 1. And the equation evaluated on the cylinder leads to the following. Here we have assumed that we can construct all the solution. We know all the solution to the lower order transport equation, and they are constructed using the previous lemma. What is relevant of this system is that at the right-hand side, you can see terms of order n, and they arise because of the cubic coupling between the Maxwell and the scalar field system. The homogeneous version of the equation is provided by this model equation. This model equation doesn't fit our previous scheme to work on the solution, so we had to find a different way to solve this equation. In particular, we recast the Frobenius method to find a solution. So we prescribed this power series solution, and once replaced into our model equation, what we found out is that we had to solve an initial equation. And with the result of this initial equation, we had to compute the recurrence relation between the coefficient to find valid series solution. What happened is for the root r equal to 0, we have no valid series solution, so we had to look for a second solution. And from here, we found a valid series solution. In particular, we found out that the recurrence relation between the coefficient gk and mk can be expressed in terms of the coefficient m0. So we have a valid series solution and only one free coefficient. This behavior, the general behavior of the coupled system, then is summarized by the solution. So this proposition. So we have a solution which is analytic for the critical set, and a solution which is analytic far from the critical set, and there's logarithmic singularity there. Well, what we can conclude is this main theorem can be summarized by this main theorem that says for generic data for the Maxwell-scalar system, which have finite energy and are analytic around the cylinder, we have this the set of transport equation develop logarithmic singularity at the critical points. So the main outcome is the nonlinear interaction makes the field more singular than what is seen when the fields are decoupled. So this provides not a really good toy model for the isofield equation, because the isofield equation show, in the isofield equation, we have a similar behavior for the nonlinear and the linear system. So our next step will be to study a different toy model, probably a Maxwell-Dirac system where the coupling is quadratic, and so probably this is a better toy model to be used to study in the future the Eisenfield equation. So yeah, this is the end of my talk.
Okay, thank you. So 1 minute over there, so we might just have time for one quick question, if anyone has one. So I just wanted to check the gauge you're using, that's the same as in Mariam's talk?
Yes, we are using the same representation of spatial infinity, and so the same gauge.
Okay, and so there's a particular reason why this is particularly useful.
Yes, because in this, as I said, once we use this gauge and use free representation, once we prescribe this expansion, we have that then we can relate the property of the relative property of the initial data with the radiative property of the solution in spatial infinity. So this is relevant from the point of view of the initial data, but also to be able to then study our system, the behavior of the system in spatial infinity, and hopefully in the future, once we find a way to deal with the logarithmic singularity and to preclude them somehow, to be able to make some estimates there.